Today we're going to finish chapter 17. Yesterday we learned about cell potentials for galvanic cells, where it's a spontaneous chemical reaction that produces electrons. So today we're going to relate that to Gibbs free energy, since they're both spontaneous reactions. And we're also going to do the reverse of a galvanic cell, which is where you have to put in electrons to make a non-spontaneous chemical reaction go. So first there's a balanced net ionic equation for you. Go ahead and pause the video and do that one, and pause when you're ready for the answer. So it says solution of potassium dichromate, that's K plus and Cr2O7 minus 2. Then it says a solution of iron 2 nitrate, that's Fe2 plus and NO3 minus, and don't forget your H plus because it says acidic solution. So it's a redox reaction because you have a common oxidizing agent, the dichromate. The thing that can get oxidized is the Fe2+, so it'll turn it into Fe3+. When the oxidizing agent oxidizes stuff in acidic solution, dichromate turns into Cr3+. Leftover oxygens and hydrogens turn into H2O, and then we have some spectator ions. We'll cross out the spectator ions, and then if you break it into half reactions and balance the equation, you get 1, 6, 14, and on the products you get 6, 2, 7. Number 2, in electrochemistry, what is N? N is the moles of electrons, because it's electron chemistry. Okay, our next objective, F. How do you calculate a Gibbs free energy for a redox reaction? So for this reaction that we used yesterday, the standard potential is 0.71 volts. It's positive, that means it's a spontaneous chemical reaction. So what sign would you expect for delta G? You should have said negative because it's a spontaneous reaction. So the equation that lets us convert between cell potential, or E, and delta G is delta G standard is negative N times Faraday's constant times the standard cell potential, where N is moles of electrons, and Faraday's constant is on your equation sheet. It's 96,500 coulombs, which is charge per mole of electrons. So we just plug into our equation, but we need the moles of electrons. We did this one yesterday. You have to equalize electron transfer, so it's 6. Instead of volts, though, it says, notice my units here, volts and moles and coulombs. Moles cancel out, but coulombs and volts don't appear to. A volt is a joule per coulomb. So joule per coulomb, that'll fix my units. And I get an answer of 410 kilojoules. If you have any questions on this one, this is a good time to pause and get your questions answered. Next objective. From a change in concentration of a galvanic cell, like as the battery runs, the concentration changes. How do you find the change in concentration of the other half reaction? For example, if we're doing that same reaction again, aluminum and magnesium, and if you start with 1 molar concentrations, what is the concentration of aluminum when magnesium are 2 molar? So it's actually just a mole ratio, but you've got to be careful with the balancing and careful with whether the change is the actual number or not. So this says it's 2, that's not the change. It's going from 1 to 2, so the change is only 1. So 1 mole per liter of magnesium ions are I had to fix that. They're formed because you started with 1 and you wound up with 2. So then we can use our mole ratio from magnesium to aluminum. But our equation was not balanced, so you got to make sure you balance it so electron transfer is equal. We did that one earlier. So you put in 2 and 3, so that's 0.7 moles of aluminum that is used, because aluminum is a reactant. So if you started with 1 molar aluminum and then you used 0.7, the answer to the problem is 0.3 moles per liter. So that's pretty easy, but be careful again that you use the changes correctly and that you balance the equation. Our next objective is really interesting. How does corrosion work and how can you prevent it? So Corrosion is another name for a redox reaction. It's most commonly called rust because we have so much iron things around. So go ahead and look at the reduction potentials table at the back of your periodic table and figure out what metals will be spontaneously oxidized by oxygen while you pause the video. So at the top, see how the reduction potentials are the most positive. That means that it's the best oxidizing agent, because that's what oxidizing agents do, is they get reduced. So it's a reduction. They're all reductions. The ones at the top are most positive. That means most spontaneous. So they're the best at getting reduced. In other words, they're the best oxidizing agents. So they can reduce things that are not as good of oxidizing agents. So there's a whole list you should have, all the metals that are below oxygen on that table. That would be all of these. And it's not important that you list every single one, it's just important that you can see from the table that oxygen is a better oxidizing agent than all of those. Most metals, when they oxidize, when they react with oxygen, when they corrode, when they rust, they develop a thin outer coating of metal oxide, like aluminum oxide, for example. Remember yesterday how our reaction didn't go until we took that coating off? So it protects most of the metal. But iron, when it does that, it makes a flaky coating that's not sturdy. So it comes off, and then the metal under it oxidizes more, and then that comes off, and pretty soon your whole metal piece is gone. So people try to prevent rusting. The most common way to do that was with paint. So it just covers up the surface, keeps it away from the oxygen. Another way that they do that is by keeping it dry, because for these half reactions, notice they have ions and even a little bit of acid, so you have to have water so you can have ions. And the last one we'll mention is cathodic protection. So for example, if you have a water heater that's made out of iron and it's filled up with water, that whole thing is going to rust away. But what they do is they put a magnesium rod inside it, and the magnesium is a lot better at getting oxidized than the iron is. So it will oxidize, and the iron won't start rusting very much until the magnesium is all gone. Okay, our last topic in chapter 17 is electrolysis, which is also very interesting. So electrolysis is used to make hydrogen gas from water. It's also used for plating silver and gold, so if you have like silver-plated spoons or something, that's the process that's used for that. And it's also used to refine metals, so you take a rock that has the metal you want in it and you melt it, and then you use electricity to take out what you want. So objective I, how do you identify the gas or solid that will collect at the positive and negative electrodes of a power supply during electrolysis? For example, if you put it in water, what would happen? So there's my leads from my power supply. Well, water is polar, so its negative oxygen side will be attracted to the positive electrode, and its more positive hydrogen side will be attracted to the negative electrode. And then let's look at the one on the left. As electrons are being added, the hydrogen gains electrons and is reduced, and the bond is broken, so you get hydrogen gas and hydroxide. We can look at that again. Electrons are added. Electrons form a new bond between the hydrogens. Bonds break. You get hydrogen gas and hydroxide. On the other side, electrons are being taken away. So that's oxidation that will occur, whereas the other one was reduction. So on the left, oxidation will be occurring at the positive electrode. And so you have electrons being taken away, a new bond forming with the oxygen. So you get oxygen gas. It's not important that you can draw animation, but it is important that you understand that water is attracted, hydrogen side is attracted to negative, and the negative oxygen side is attracted to the positive one. So those are the ones that get reduced or oxidized. Let's look at another example. What gas will collect at the positive and negative electrodes of a power supply in a solution of sodium chloride? So, The sodium is positive, so it's attracted to the negative electrode, and it'll get reduced by those electrons, turn into sodium metal. The chlorine is attracted to the positive electrode because it's negative. It'll lose those electrons and turn it into chlorine with zero oxidation state, which is diatomic, so it's Cl2. However, that's not the answer to the problem because sodium is not going to stay there. Sodium reacts with water. We've done this one many times. So it makes hydrogen gas. So the gases for the answer to the problem are hydrogen and chlorine. Okay, last for this chapter is doing conversion factors to convert between kind of like plating out a metal, for example, is this first example. How much time would it take for a current of 5 amps to reduce 10.5 grams of silver plus ions to silver metal? So if you just like put a spoon in your silver plus solution and connect it to your power supply, the silver ions would plate right on there. So we're going to know a couple of things first, that we need a balanced chemical equation and that amps are coulombs per second. In these problems, it works out the neatest, the most fluid if you start with grams or time. In this problem we have grams, so we'll go to time. Other problems give you time, so we'll go to grams, the reverse. And then the amps are kind of like a conversion factor because look, they're coulomb per second, so you'll use those to convert in between. So we'll start with our 10.5 grams of silver and we'll convert to moles. So once we have moles of silver, we're like, what can we convert to? Well, moles of electrons, because that's related to amps. So use your balanced chemical equation. It's not always 1, but in this case, it's 1 mole of electrons. And so now we have moles of electrons. We're like, what can we convert to? Well, you can convert to charge, because amps have coulombs in it. And it's a conversion factor that's on your periodic table. It's called Faraday's constant. It's on your equation sheet. 1 mole of electrons is 96,500 coulombs. So now that I have coulombs, I can use my amps conversion to go from coulombs to seconds. This problem says 5 amps, so that means 5 coulombs per 1 second. So I'll put 5 coulombs on the bottom, 1 second on the top. Finally, the problem says find it in minutes, so we'll convert to minutes. And we get 31.3 minutes. Let's do another example. Last one. This one gives you time in amps asked for mass. Again, these problems are easiest if you start with mass or time. So start with time. I'm asking myself, what should I convert to from minutes? Well, I have amps. Amps are coulombs per second. So let's go ahead and convert to seconds. Then I can use my amps conversion, which is 150 coulombs is 1 second. Next, from coulombs, I'm asking myself, well, what can I convert to? Well, moles of electrons. That's Faraday's constant. Now I have moles of electrons. I'm like, I better use my balanced chemical equation because it has moles of electrons in it. Use the half reaction. So it says 2 moles of electrons, 1 mole of Pb. And finally, we'll convert to grams and get our answer. So it is 140 grams of Pb, lead. So there's a bunch of book problems for you. Work on those, and also make sure you finish your Chapter 16 terms if you haven't already, and I'll check those on Monday.